So the full completed assignment is now posted. We'll have our problem session tomorrow morning at 10 o'clock in room 190. I made some annotations to the set of notes for, so you might want to reload them again, and the next set is posted as well. All right, let's see where. Firstly, I want to address the flub of the beginning of last lecture and see how it works out, how it's supposed to work, and what I messed up the last lecture in my mind, and therefore here. Okay, so just quickly, we have our operator ordered representations here of an operator. So we have, for example, operator that we can express as a power series in different operator orderings. This is a normally ordered power series, and this is a anti-normally ordered power series. And the representations that correspond to the normally ordered representation and this anti-normally ordered representation is obtained by making the substitution that A dagger goes to alpha star and A goes to alpha, okay? And that can be obtained formally by tracing the operator with this operator T, which is a delta function that, assigns A dagger to alpha star and A to alpha with the particular ordering. And in fact, you have to trace it with the dual, which is with the minus sigma, okay, to pick off the sigma representation. And I wanted to show you, and I messed it up last time, so let me show you now, how that follows quite simply, okay? So if we just let's look at, for example, let's look at the, either one. Let's start with, say, the normally ordered guy. Okay, so that's equal to the trace of A with the anti-normally ordered version of this, right? Which is pi A minus alpha, A dagger minus alpha star. That should pick it off. Now let's see that works. That when I do that trace, I'm going to return this with the case of the normally ordered coefficient. So I'm just going to plug in this equals that. So I'm going to plug it in. That's what I did last time. So that's equal to the sum over n and n, c n m plus 1 pi the trace of A dagger to the n, A to the m delta A minus alpha delta A dagger minus alpha star. Okay. Right? Just plugging by the definition of what we just, just putting in that expansion. Okay? Now, here's the trick, which I didn't see. I'm going to take this trace. This is cyclically permutable. So I'm going to put all the A daggers on the left, which I can do. And that's what I forgot to do. I jumped in the identity too early. So I could look at this and then say that this is equal to nm c nm plus 1 pi the trace of A dagger minus alpha star A dagger to the n, a to the n, delta function a minus alpha, right? That's just cyclically commuting, which we're allowed to do. Now I can do the trace easily, because this trace so that says that this representation for normally ordered is the sum over n and m, c n m plus 1 pi, and that trace I can obtain by using the coherent state representation. So I'll plug that in. So this is a dummy variable, alpha prime, delta, a dagger minus alpha star, a dagger to the whatever power that is, and a to the m, delta function, a minus alpha prime, right? That's the trace. I see some puzzled looks, so if you have a puzzled question, ask me it. I just took the trace, which is just summing over the diagonal elements, which is what it is in the coherent set representation, right? And now this works. Now I replace this guy. This gets replaced with alpha prime. This gets replaced with alpha prime to the m. This gets replaced with alpha star to the alpha prime to the m star alpha prime. Get rid of that stuff. Now it's all numbers. Sum and integrate. The pi's cancel, and voila, I get what I wanted. Okay. Similarly, if I come back over here, and I'm going to say, which you already do, make this a -1. Make this a dagger, make that a star, do that, right? That's what you get to where the, now that is, I'll put this c to the -1, a dagger to the n, dagger. Okay, so now I just look at that guy, now what? Any suggestions? How am I going to take that trace? Well, now I can just do the cyclic permutation, put this guy over there. And the same thing follows. And I'll pick off that coefficient. So, indeed, it is as I was trying to say last lecture, that the act of tracing with the appropriate delta function does exactly what you want it to do. It substitutes a dagger for alpha star and substitutes a for alpha in the appropriate order. Okay? All right. So let's finish up our discussion about this. So based on this, we have a kind of now representation of operators in phase space. Okay? And based on that, we can, for example, as we discuss what that implies, for example, if I look at the expectation value of some observable, which is the trace of rho with A, that could be expressed in a phase space representation as the integral over this case, this is like that. Phase space representation of the state with the phase space representation of the operator with the opposite ordering. Okay? So this is a statement of the more general expression that says if I look at the inner product between two Hermitian operators, they don't have to be Hermitian, but I just don't want to deal with complex conjugates all over the place. It's just, otherwise I'd have to put a dagger over here and think about the stars and all of that. That this is equal to the integral so it's a general expression of how you look at the inner product between the two operators based on the so-called Hilbert-Schmidt inner product in terms of the representations on phase space. And they come in these different ordered pairs between them. So this has implications, and the reason the pi is missing here is that, you know, there's a factor of 1 over pi in how the figure function is defined. Okay, it's not uniformly defined that way, but I'm defining it such that what this says is the inner product of rho with rho, or said another way, I don't really want to say that yet. What I want to say is the trace of rho, as we discussed last time, is equal to the integral over, which made this normalize in that way. That's why the pi is absorbed. Otherwise, you might have a 1 over pi here. Okay, this is defined this way. So, the physical implication of this that we discussed last lecture is that depending upon what operator ordering is relevant in the observable, determines what operator ordering is relevant in the representation of the state. So when we talked about coincidence counting of photons, the operators there were normally ordered operators. That's what Glauber's theory taught us. Glauber's theory taught us that to calculate the expectation value of the rate of coincidence counting of counting photons, the observable that's there was a normally ordered product of A and A daggers. And so we can calculate that in terms of an average in phase space with the anti-normally ordered representation of the state, which is, which one? PQ or W? The anti-normally ordered representation of the state is the Glauber, right? So again, Q is equal to the normally ordered rep of rho. And of course, that's the same thing, as we know, there's so many different relations here. So many. When I take that trace with t minus 1, it's the same thing as that, right? That's the same thing as taking the trace. And then P is the anti-normally ordered, and W is the symmetric. And they come in this pairs. If I want to think about a normally ordered representation of the operator, I have to pair that with the anti-normally ordered representation of the state, which is why the P function appeared in Glauber's function, in Glauber's theory. And we talked then about non-classical light as, in the Glauber theory, as states of light that can't be expressed as a classical P representation for those kinds of experiments. If we were talking about homodyne measurements, not photon count experiments, then the natural representation is the Wigner representation. Okay? Because the quadrature operators are naturally symmetrically ordered in A and A dagger. So if you look at, say, the quadrature x squared, that's going to have all the symmetric powers of A and A dagger in them, right? The cube function, on the other hand, doesn't seem to naturally come with either of those, although it is, in fact, this is the trace of rho with this thing, right? Which itself is an element of what we would call a POVM. That is to say, this forms a resolution of the identity. So these set of operators represent some set of measurements I could do with outcomes that somehow are both x and p at the same time. Can we do such a measurement? I'm doing it right now. Looking at your position, your momentum, and saying, okay, I could do it. It's not a measurement of a Hermitian observable. It's a more generalized measurement. But it's one we do all the time. And this is actually related to what's called optical heterodyne. It's supposed to be homodyne. A heterodyne measurement is described actually by this POVM. With these measurement outcomes, we have both quadratures simultaneously, but it's a kind of measurement that is noisier. We have homework problem on that. Right, okay, so what we also discussed last time was the question of whether or not these representations exist or not, whether they converge or not. And whether or not they exist or not depends on whether this is a convergent integral. Okay? So we talked about bounded operators as ones whose Hilbert-Schmidt norm and I could do that for, say, the symmetric representation is finite, bounded. Okay? So if that is a finite number, then we say it's a bounded operator, and this thing then is a good representation. Okay? Now, for the case of the density operator, the norm squared of rho is the trace of rho squared, which is always bounded. Therefore, what that tells us is that the Wigner function, which is the symmetrically ordered representation, always exists and is a good function. It's a nice, well-defined function. Now, on the other hand, the Wigner function can be negative, and as we discussed last time, what that's telling us is that quantum mechanics doesn't allow a classical statistical theory where we just assign some probability of having x and p simultaneously in a general case, right? We can do that in some cases, and the only case we could do that if rho is a pure state is if the Wigner function is Gaussian. And those are the states that are related to the Swede states. We call that the Hudson-Piquet theorem, to be fancy. On the other hand, the other functions, well, the other thing we defined was the characteristic function, which is the Fourier transform of the quasi-probability distribution. It's the thing that we said we use in statistics And the characteristic function itself is another way of expressing the inner product. That is to say, and I probably get the factors of pi wrong here because of the fact that the bigger function has this absorbed factor of pi in it. But I think this is actually, in this case, let me double check it. It should be pi squared. One of the annoyances here.
You said pi last time.
Doesn't mean I was right.
If you take something that's sort of mean like Fourier transforms, then it shouldn't be not like you could put like,
Yeah, I guess this is the way I've defined it, so yeah, I think this is fine. Yeah, it's just really, yeah. Right, so that tells me that this is, we can also think of, you know, this in the, I'll call this in this case, the Fourier transform here, a tilde, it's the equivalent thing. What we discussed last time was that the characteristic function associated with the Q function is related to the characteristic function of the Wigner function by this exponential factor. Yep. Mm-hmm.
So last time it turns out you defined W sigma with the pi and not chi. Not that's similar as chi, right?
Yes, that's chi.
Chi. But now we are defining chi with the pi and W sigma with not the pi.
You see, one is the one. They both have pi in this way. If I define it this way, then this is of course the inverse Fourier transform will have this. But I don't want to get stuck on minus signs and vectors of pi. I just don't do that.
Okay.
All right. So I want to get to the important physics, not these details, which we can fix. The characteristic function, this is the characteristic function associated with the Q function. That's the normally ordered representation. And this is the characteristic function associated with the Wigner function. That's a symmetrically ordered case. Because of this fall off, this guy is going to be a bounded function, which says that the Q function also always exists. On the other hand, if we look at the anti-normally ordered guy, which is the case of the P function, that would be a plus, right? And for that case, what we see is that in order for this integral to be bounded, this thing has to fall off extremely rapidly, which means that the anti-normally ordered case, the P function, rarely exists. It has to fall off. It's only the case when the Wigner function, characteristic function, falls off at least as fast as the Gaussian, in order for that to be true. Okay. So what that says relative to what we were looking at over here is that even though it might be the case, for example, we can always say, let's always use the Q function, because the Q function always exists and it's always positive. So we should be able to have a nice representation of quantum mechanics in terms of classical probability, because the Q function is an honest-to-God probability. Not so fast, because the representation of the operator won't exist necessarily. So there's no hiding here. We can't shove generally quantum mechanics into classical theory. But sometimes we can. And so one of the things that we've come to understand and learn over the last number of years, I would say within the last decade or so, is that the non-classical nature of certain systems can be a resource for doing things that are not possible if the system obeys the logic of classical probability. But sometimes systems do obey the logic of classical probability. So we want to, try to understand where that border is and where that power lies. That continues to be a challenge. What is the power? What systems give us the power to do things that we couldn't do? Quantum systems allow us to do things that we couldn't do with classical physics. All right, now you have, I guess there's a couple of little things I want to say just to complete this, just for usefulness and actually doing the calculations, actually calculating these functions. How do you do it? Well, there's lots of different approaches. One thing to note here is because of these relationships that exist between the characteristic functions, there's different relationships between the P and Q functions, right? Because I could just substitute in the characteristic function of one for the other. So, as we were just saying, for example, if I look at say the Q function, that's the Fourier transform of its which I can write as that, right? But then I could substitute this itself as the Fourier transform of the vector function. So this gives me a relationship between the Wigner function and the Q function.
Excuse me.
Yes, sir.
The relation between quasi-probability and
I'm sorry,
characteristic.
+1.
Yeah.
Thank you. Yeah, thank you. Absolutely. So let me try to get this factor right for a change. So this is equal to, when you do that integral, 2 over pi, the integral over beta, the convolution with the Gaussian. Okay, this says what? It says the Q function is a kind of coarse-grained version of the Wigner function. I'm looking at the Wigner function at every point beta, and I'm multiplying it by a Gaussian function with a certain spread, and just sort of smearing it out. Is that clear that that integral is a smearing over a Gaussian? Right? I see faces like, what are you talking about? So, that's just a convolution, right? I'm smearing out the point. If this were a delta function, it would just return it, but this is smearing it. So this is a kind of smearing of the delta function. Moreover, you can look at it, you could do the same kind of thing. You could say the Wigner function is a smeared version of the P function. By the same argument. Or this is the Q function is a doubly smeared version of the P function, smeared with a wider Gaussian. And that's equal to this. It has a broader variant. I have that function over here. This is the P function. Okay. So each of these quasi-probability distributions are related to one another in this way. This guy, because of this factor, even if this is some horrible derivatives of delta function thing, this thing will be a well-defined function. Interesting. Now this gives us lots of different paths to actually calculating these functions. How would I do it? Well, one way to do it is I calculate the characteristic function, and then I could do the inverse Fourier transform. Or if I have some way of calculating, say, the P function, I can then quickly get the Wigner function and the Q function, right? So there's lots of different paths to going about this. Of course, remember the characteristic function here is equal to the trace of rho. This is the expectation value of D. This is typically the path one would take when we just calculate that expectation value and then do one of these Fourier transforms in order to come up that function. Let's do a very simple example just to conclude. Let's say the state is a coherent state. What is the P function?
Like specifically?
What's that?
Would it be another Gaussian?
Yeah, kind of. I think that's reasonable. But we should be able to just write it down without doing anything. Now, how is the P function? P function, of course, is the anti-normally ordered representation. I could do it delta. But sometimes I can just look at it and see the answer. Why? Well, rho, in this case, is this, right? But if in the P representation, what is rho?
It's a delta function.
Exactly, because you look at this is the definition. Remember, that's the P representation.
Because it picks up.
Well, this is the definition of the P function, right? The definition of, well, not the definition. Let me say, why is this always true? Well, that's what we wrote down as originally said Glauber's definition of the P function was it was a statistical mixture of coherent states. But how does that fit into our whole horrible formalism? Well, what we have is that rho is equal to the integral over alpha, the trace of rho with T minus sigma of alpha, T alpha, sigma alpha, right? That's the general formalism. If I make this -1 and this +1, right, then this thing is equal to pi times that's what we had earlier, and this guy is the P representation. Pardon me, this guy doesn't have a pi. So it fits into our general formalism. The representation is, this is the anti-normally ordered rho with the normally ordered t's. But getting rid of all that stuff, this is how we wrote it down originally. Okay, so now someone said a delta function. What's P of alpha? please.
Delta, alpha minus alpha naught.
Thank you very much. I appreciate that. This is kind of a Gaussian, but it's a Gaussian with zero width. So the P representation is the limit of a Gaussian. I'll give you that. That's good enough for me. So the P representation, the quasi-probability distribution is a point right at alpha naught. Okay. What about the Wigner function? How would you get it? How would you? Well, one way to do it is this. I mean, I could go through the Gaussian integrals, but since I already know the P, if I know the P representation, then I'm done, because I get to just convolve it with the right Gaussian to get the other guys, right? So this tells me that the Wigner function, according to that formula over there, is equal to 1 over pi e to the minus alpha naught squared. Right?
What is the equation for W versus P? The last line or the?
That's this guy. This is.
I think that was Q, right? In terms of P.
Yeah, you're right. Thanks. Thanks. There's a factor of 2 there. Absolutely. Thank you. Correct. That was the Q function. Well, we wrote down the Q function. Well, what about this? Now, is this right? Well, we better be the case that the noise in X and P, the variance in X and P, is what we expect it to be, which is 1 over root 2, right? So I can write this, remember alpha is X plus IP over root 2. So this is equal to 1 over 2 e to the minus x0 squared times e to the minus p0 squared, right? Times a factor of 2 up there. Right, this way. So that means that W of X and P is equal to this. Right, because it must, when I make the change of variables, alpha, there's a factor of 2 there because alpha is equal to X plus IP over root 2. Okay, so integrate, yep.
Why does the 2 out front go away?
Yeah, it's a good question. The reason is the following. Because we define, it's really just a definition here, that we have defined this guy to be equal to x dp over root 2, just get rid of that, right? Times w of alpha. We combine all that together. We absorb that half into the w so that when integrated over x and p, this is normalized. So it's just a Jacobian.
Okay.
That's where that's just the way we want this to be normalized. So we absorb the half into that. Okay? Good. So now I ask you, does this have the right variance in x and p? How would you know? Yeah, well, everyone has memorized this. Absolutely everyone has memorized what a Gaussian is, right? A Gaussian is normalized such that the probability of the random variable is 1 over root 2 pi sigma squared e to the minus x minus the average x squared over twice sigma squared, right? Where that's the variance, right? So I can write this as 2 sigma squared, root 2 sigma squared, 2 sigma squared, 1 over root 2 pi sigma squared, if sigma squared is a half. And it works. So indeed it's true. It's a Gaussian. In fact, it's a circularly symmetric Gaussian with RMS width in x and p, which is 1 over root 2. Okay. And the Q function was basically this smeared out a little bit more. It'll have a width that's wider, it has excess noise in it. But those don't represent the variances in x and p, because you don't, the Q function does not marginalize to the right probability distribution over x and p. Only the Wigner function marginalizes properly. If you wanted to find the variance of x using the Q function, how would you do it? Well, you have to find the anti-normally ordered representation of x squared and average that with the Q function. Okay, which you could in principle do by finding the characteristic function of x squared with the anti-normally ordered product and all of that stuff. Yes, Steve?
I might get into this later, but I mean, I feel like I can understand what, the Glauber, right, that's the P.
Yeah.
Am I remembering that right? Okay, I can understand what that does, I understand what the Wigner function kind of is, but the Q function, I'm not, I don't know if we're going to get into that, but it's harder to understand maybe
It is.
what it tells you.
It doesn't tell you much, is the answer. It is, as I said, and this is not particularly useful, it is a probability distribution, because it's always positive. And it corresponds to the probabilities of outcomes of heterodyne measurements. Okay?
Okay.
So if you were to do heterodyne measurements, they would come out with a probability that is related to the Q function. The Wigner function is telling you its marginals, which are probability distributions, tell you about the probabilities of outcomes of homodyne measurements. Okay?
And so that's why the Q function is turned out more, because it's noisy.
That's right.
Okay.
Because the heterodyne actually has both x and p at the same time, and there's no way to do that without excess space.
Okay.
Yes, sir?
So formally speaking, does it make sense to talk about undoing these convolutions?
Oh, well, we can always do that in principle, right? I mean, one way to do it is you can always invert it by taking the Fourier transform, right? Which is how we got it in the first place, of course, right? So you can deconvolve by taking the Fourier transform and then dividing by that thing, and it gets on the other side, right? So you can take the inverse if you like. Of course, so yeah, but the problem is, if I were to try to relate the P function, say, to the Q function, it's going to be the convolution with something else, which is the convolution with the inverse Fourier transform. Think of that. But that thing's not going to exist. It will exist as a formal delta function type doohickey, but it's not going to be an honest-to-God function. But we could write it down formally, and what we would then see is, for example, generally the P functions are going to be horrible derivatives of delta functions of the Q function, which is they don't really exist. They're just symbols that we're writing down, but they're not good functions. All right, good, excellent. All right, so we're going to have lots of practice of this kind of thing in homework, and you'll see it a lot more. All right, let us then talking about classical versus non-classical in the context, essentially, of a single mode of the field, right? And we've talked about properties like self-Poissonian statistics or negativity in the Wigner function, and those are properties of what you might call a single degree of freedom of the field, one mode, if I think about a mode as a degree of freedom. But of course, there are other ways we characterize classical and non-classical, particularly for multiple degrees of freedom. And one of the most important and interesting one is the question of entanglement. So we're going to spend the rest of the time before spring break talking about entanglement.
That was a long class.
What?
Spring break.
Did I say spring break?
Yes. I signed up for a bond.
We're going to keep on going. Spring, fall,
Plus
very
minus.
sage time. All right. So, of course, this is a big subject. We're only going to touch on certain aspects of it, but entanglement has played a very important role in the development of quantum optics. You know, as you may know a little bit about the history of this kind of thing, and Bell wrote down, well, of course, entanglement goes back to Schrödinger and Einstein, Godolphin-Rhodes, and famous Gedanken experiment, looking at trying to address the question about whether quantum mechanics can really be a complete theory of the world. And it kind of laid fallow until Bell picked it up again in the 1960s and really addressed the issue of the question of whether one could see in an experimental context a distinction between quantum theory and a desired realistic statistical model of the world. But that too kind of laid fallow for a while. It was thought of as a kind of curiosity until, you know, the hippies saved physics. Well, or so the story goes. There was then a desire, you know, maybe about, I don't know, a decade or so after, in the early mid-1970s, to try to see whether one can really do a test of Bell's inequalities. And the natural forum for testing Bell's inequalities was with photons, quantum optics. And so quantum optics became the arena in which people who were interested in addressing the questions of the foundations of quantum mechanics found themselves. And that's how I ended up in this field, because that was really what my interest was as a graduate student, as many of your interests are. It's a fascinating question. So as the subject developed, in order to do those tests of Bell's inequalities and other questions in the foundation of quantum mechanics, new experimental tools needed to be developed to be able to prepare, control, and measure in a very precise way individual quantum systems, individual photons, individual atoms. This was not what, you know, the idea, I mean, of actually measuring an individual elementary particle or like a photon or even an atom was considered absurd back in the 1920s, so they didn't really worry about this kind of thing. But then as the technology developed and people started to say, well, can we do this? Then we really had to probe what it meant to really measure a quantum system and so forth. And that, in some sense, that was recognized in 2012 in the Nobel Prize that was given to Dave Weinland and Serge Roche for manipulation of individual quantum systems. Because that was an important tool. Now, that then got into the latter part of the last century, in the 1990s, and moving forward to the present, the ability to manipulate individual quantum systems and understand what it meant to measure them really morphed into quantum information science. Because over time we understood that when we had this control for individual quantum systems, we could do things with them. It wasn't just the curiosity of understanding the nature of physical reality, which we care about deeply, but it also had this sort of practical implication. So quantum optics has kind of morphed into quantum information science. Pretty much everyone who was working in quantum optics took their tools and are using them in the context of quantum information science. So entanglement has played an important role in the stream of connecting all those things, where we are in the present and how we got here. All right, so with that kind of preamble, what are we talking about when we're talking about entanglement? Well, when we're talking about entanglement, what we're thinking about is quantum correlations between different degrees of freedom. Okay. So let's just think about the simplest possible case. Let's just say we have two particles moving on a line. Those are my 2 degrees of freedom. Each particle can have a position classically and a momentum. So these are my 2 degrees of freedom. Okay. Now, if I want to look at those 2 degrees of freedom, quantum mechanically, I might look at, say, the joint wave function, now not in terms of phase space, although we might get to that. We just have, this is the wave function that represents the joint probability amplitude to be at position XA for particle A and XB for particle B. Okay, that's a perfectly good wave function we could write down. And from that, we can determine the joint probability density. Let's call this capital psi. Which is that. Right? Now, the question we can ask ourselves is, under what condition is the joint probability statistically uncorrelated? That is to say that this probability density factorizes. Okay? If that's true, in this case, if and only if the joint wave function is the product, and this doesn't have to be the same function, call it P2 different functions. So this is my joint probability. Some psi A at function, and some psi B as a function of XB. So that's the only way that that could be true, or if the joint wave function factorizes. And we would say in this case that the system is separable. Okay. So if the joint probability density arises from a pure state of this sort, then the only way that it could factorize into joint probabilities is if the wave function factorizes, in which case we would say the system is separable. If this is not true, so for a pure state, if the joint wave function for the two particles, the 2 degrees of freedom, does not equal the product of two wave functions, then we say it is entangled. Now, more generally, if we don't want to just think about motional degrees of freedom, we want to think about spin degrees of freedom or other degrees of freedom, we typically would want to formalize this more generally in Hilbert space. By writing, say, a Hilbert space associated with 2 degrees of freedom as the tensor product space. So in this case, we have 2 degrees of freedom. Which are sometimes called subsystems. So I'm using the term degree of freedom and subsystem interchangeably. What we call subsystems in quantum mechanics is what we call degrees of freedom in classical mechanics. Okay. So this would be an example of what is called a bipartite joint system. It has 2 parts, A and B, that are distinguishable, and we can write them. For example, this could be the position of particle A and this position of particle B. Or it could be a particle moving in 2 dimensions, where this would be, say, the x degree of freedom is the y degree of freedom. Or it could be the position and spin of a single particle. That's another example of a bipartite system. Right? All of those are examples of 2 degrees of freedom. And if we had multiple degrees of freedom, we would have it. Now, of course, to remind you what the tensor product space, how it's defined, so let's say that HA, to start, although we can generalize quickly, we'll start to say that HA and HB are finite dimensional. So that might be the case, for example, of, say, the nuclear and electron spin of an atom, for example. And let's say the dimensions are dA and dB. They may not be equal. So we would say have a basis for Hilbert space A and a basis, I'll call it F, B, squared over space B. Then a basis for the joint over space is the tensor product space. And so I could just take the, I'll call ij ei tensor fj. And the dimension of the joint space is what? dA times dB. Thank you very much. Right? Those are all the basis vectors here. The product of the dimensions is the dimension of the joint Hilbert space. Okay? So now, I can ask, for example, about the probability if I have some state on the joint Hilbert space. I can ask about what, for example, the probability amplitude in this particular basis, right? And then the probability to have those two guys, and of course, is the square of that amplitude. This is all. So now, if I wanted to ask what is the marginal, what's the probability of seeing outcome I on system A, right? This is joint on A and B together. So I want to know what is the probability, so this is a joint probability on the joint system. I want to know what is the probability to find outcome I if I just do a measurement of system A, and I don't care what happens to B. How can I determine this probability distribution?
Just sum over all the space that we could be in.
That's right. So I marginalize, right? So I would sum this over J equals 1 to dB of the joint probability distribution for the two. Okay? That's the marginal probability distribution. Now, as before, as we said in the context of the wave function picture, the question is when, if the joint state of the system is a pure state of this kind, when can I think about this as equal to the probability amplitude squared of some state? When is that true? If it's separable. So this is true if and only if psi of the joint system is a product state for two different states, or they could be the same depending on kind of Hilbert space. Okay. That's the only case. In this case, we would say the state is separable. Otherwise, entangled. So, given a joint state of the system, a general joint state. How do I determine the state which may, for this moment, let's start general pure state. Okay, it might be entangled. I will generalize in a moment this to the joint state being possibly mixed as well, but let's just start here. Okay, so let's say we have a general pure state of the joint system. And I ask you, how would I find the state associated so I want to know what is the marginal density operator. Just like we had the marginal probability distributions,
You trace over the.
we have some notion of the trace. So let's see how that worked out. I mean, this is the object which is supposed to give me the probability of, say, finding outcome I in the basis state I was equal to, supposed to be equal to this. Right, that's right. And there are coherences as well. Well, if I look at this guy over here, I can look at the general density matrix. That's the density matrix in the standard basis that we wrote down. And from this, I want to, so if I looked at the, for example, if I looked at this probability distribution, I could see the following. So the joint probability density, or distribution, in this case, not a density, these are discrete variables, is equal to this. And the marginal was sum over J. Right? And that is equal to the trace over the second interval. Right? So this would be equal to so this is the sum over J of that, which is the trace over system B of the joint system, and then looking at that probability. What does tracing over system B mean? It means summing, so the trace over system B in this case is the sum over J, Fj, rho AB, Fj for system B. That's what this is. Because when I plug that in, I get that.
Excuse me.
Yeah.
The subscripts of rho, aren't they supposed to be AB? So?
This guy should be AB indeed.
And there as well on the beginning of the line, yeah, probably.
Where?
Over there.
Over here, yes, thank you. Yep. Indeed. So, we get the marginal, the state, the marginal density operator here is the trace over system B of rho AB, which is given by this expression. Similarly, the marginal density operator for system B I obtain by tracing out system A. So, if the state of the system is separable, let me call that psi, let me call this phi. The joint state of the system can be expressed like that, right? So now it's obvious, here, that be there. If I do the partial trace, say tracing over system B, what do I get? Well, tracing over B gives me that, which is the pure state for system A. And similarly, if I trace over system A, now I trace over A,
I get that.
so when the joint state is pure and separable, the marginal states are also pure. Right? On the other hand, if the joint state is entangled, what does that tell me about the marginals? Suppose, let's consider two spin 1/2 particles. So I have my joint Hilbert space is the tensor product space of two spin 1/2 particles. Okay? And let's suppose psi is say, this state. It's a fine state of the system. This state is entangled, right? There's no way to write this as the product of two wave functions or states, one for A and one for B. The joint density matrix, of course, density operator for this system, is a half A tensor for B plus a half up for A tensor. Sorry, it's got them down. Tensor down. Minus a half up, down, A tensor up, down, B, minus a half down, up, A tensor down, up, B. Right? Do you agree? So, what is the marginal state for A? I trace out B. That gives me a half up, plus a half down. What about this?
It's 0.
That's 0, and that's 0.
Right.
Similarly, this is of course that shouldn't say B, that should say A. The identity operator times a half on A. And if you do the same thing, you marginalize B, you're going to get that. So what we see in this case is that for this particularly entangled state, the marginal density operator, even though this is a pure state on the joint system, the marginals are mixed. Not only are they mixed, in this particular case, they're maximally mixed. They're as mixed as they possibly can be. There is no coherence left in the marginal states, which is, as we will see, an indication that this thing is maximally entangled. So one of the most bizarre things we see in quantum mechanics, and this is an indication, is a situation where the state of the whole system is as well defined as it possibly can be, meaning that the joint system is a pure state. Pure states mean we have the maximum possible description of the system that we could have, consistent with quantum mechanics. But even though we have the maximum possible information about the whole, we have the minimal information about the pieces. The pieces are completely incoherent. The pieces, we have the minimal information. That's something that is unique to quantum mechanics. You cannot have, in classical physics, a system where we have complete information about all degrees of freedom in a joint probability distribution and have completely no information about the pieces. Somehow in quantum mechanics, the information is in the correlations. Okay. So, I just want to, we'll just spend 2 more minutes just to say one more thing. Let's consider another example. let's say the joint system was the following. Right. Let's consider that state. Is this state entangled? Sure looks like it, right? But in fact, it's not. This state is equal to 1 over root 2 It's a product state. It's a product state of spin up along X and spin up along Y. I kind of just fooled you by writing it out in the Z basis. And when we looked at it, if we couldn't see how it factorizes, we might look and see that it's entangled. So where we're headed now, we need tools to somehow deduce whether a state is entangled or not. Because we may be able to do this by eye, but we may not. And then to deduce how much entanglement there is in the system. We have a clue here from this example that the entanglement in our pure state is related to the mixedness of the pieces, right? When we had a pure, separable state, the pieces were pure. When we had a state that is, in this sense, maximally entangled, the pieces are maximally mixed. And we want to quantify that, and we'll do that next time. All right? Very good. There is a C-Quick seminar starting in 7 minutes, which you may be interested in attending.